Hello and welcome to the 3.1 day 3 video. Congratulations, you've made it to the end of the 3.1 notes. Today we're going to be going over examples 4, 5, and 6, which is all about looking at a graph and writing the equation. But first it wants us to list a few different features. But the nice thing about this is that, I'm going to try to zoom in. The nice thing about that is that you can just kind of look at the graph for all of these features. So let's see, it wants us to list the degree of the polynomial, long-run behavior, maximum number of turning points. We're also going to list maximum number of zeros, horizontal and vertical intercepts, zeros, and their multiplicities. And then we're going to go through and find all of our information and the equation. So for the degree of the polynomial, we need to go through, look at all the zeros, which we have here, here, and here. And look at their multiplicity. So we're going a little bit backwards. I noticed that each of these goes straight through the graph. There's no curve, there's no bounce. So since each of these three roots or zeros just goes straight through like a multiplicity of 1, we're going to say this is a degree 3 polynomial. And the long run behavior, you can just kind of look at the graph to see this. So first we're going to say, as x goes to negative infinity, which is just our left arrow, well, that left arrow is facing downward, so we're going to say f of x goes to negative infinity, so that means it's going down since it's negative infinity. And then for our right one, as x goes to positive infinity, or the right side of our graph, f of x goes to positive infinity, meaning it goes up. So that's what this information is saying here. The left side of the graph is going down, right side of the graph is going up, but this is the proper notation that we would use. Next, we're going to list our maximum number of turns, which is 1 less than our degree, which in this case will be 2. And then the maximum number of zeros is the same as our degree. So in this case, we actually have the maximum number of zeros. We have 3. The last few things it wants is all of our intercepts. Fun thing is we don't have to solve for anything. We could just look at the graph. So the vertical intercept, in our case, is at the point 0, 0 on our graph. We can clearly see that. And then our horizontal intercepts are at negative 2, 0, 0, 0, and 3, 0. So we can see those on the graph. We've already actually kind of marked them up. And then our zeros is essentially the same information, but with x is equal to. So we'll have x is equal to negative 2, x is equal to 0, and x is equal to 3. And then underneath, we'll list all of their multiplicities. We've already kind of talked about this. Since all of the lines are going straight through the graph, they all have a multiplicity of 1. So this is the important information that we need. So if we're going to kind of mock up an equation, it might look something like this. So f of x is equal to some a value, I don't really know what, some leading coefficient, times x plus 2 times, and then you can do like an x plus 0 times x minus 3. Now the way that I got each of these factors was to take my zeros. So for instance, I'd look over here at x is equal to negative 2, and I would add 2 to both sides to get it equal to 0. So that's how we got x plus 2. Here, you can just write this as x or as x plus 0. Here I subtracted 3 on both sides to get x minus 3. And again, each of these has a multiplicity of 1. So the question is, what do we do? How do we solve for that a value? Well, we're going to be using this given point right here on our graph. So in our case, 1, negative 3. So we're going to use this given point to solve for a. So use this given point to solve for a. So I'm going to plug -3, where my y value normally goes, is equal to some a value. And then everywhere I see an x, I'm going to put in a 1. Oops, color coding. All right, so I've plugged a 1 everywhere I see an x, and now I'm just going to solve. So let's see, we have -3 is equal to a times 1 plus 2 is 3, times 1 plus 0 is 1, times 1 minus 3 is a -2. Let's see, 3 times 1 times -2 is going to give us, I'm going to move this up a little bit, let's see, -6. And then once I divide both sides by -6, I'm going to get that a is equal to 1/2. So I've been able to solve for my a value, but I'm not going to stop here. I want to rewrite my full equation, and there's a few different ways you can do this. So I'm going to write f of x is equal to 1/2, that's my a value. And then you can keep the factors the way they are, or I'm going to just take my x plus 0, and I'm going to move that just to be x up at the front. And then x plus 2 times x minus 3. Those factors can be in any order that you want as long as the 1/2 is in front. And then if you'd like to include the multiplicities, you can. If it's any number other than 1, you have to include them. But for 1, you don't necessarily have to. But that's all you have to do. That's us finding our equation. Now let's do that twice more. Now the next problem is a little bit more exciting because it has a few different multiplicities going on. Now, I'm going to start actually with my horizontal intercepts just to kind of show you what I mean, and then we can go back to our degree. So let's see, I'll start down here. Hopefully it'll leave myself enough space. For our horizontal intercepts, again, I see we have 3 of them here, here, and here. So we have 1 at -3, 0, again at 0, 0, and at 3, 0. So when I write out my zeros, it's going to be x is equal to -3, x is equal to 0, and x is equal to +3. Now when I look at the multiplicities here, I'm going to look at the behavior around each of these. So if I take a look at x is equal to -3, right here I see a bounce. It does not go straight through the equation, and I see the same thing over here around 0. So it looks kind of like a mini quadratic. So each of those are going to have a multiplicity of 2. And then over here, when x is equal to 3, it just goes straight through. So that's going to be our multiplicity of 1. So things are getting slightly more exciting. But now if we remember, we can take our multiplicities, add those together, and that's going to give us our degree. So in this case, the degree is going to be 5. Even though we only have 3 zeros, or 3 horizontal intercepts, we still have a degree of 5. With the long run behavior, that says as x goes to -infinity, f of x goes to infinity, which means that on the left side of my graph, the arrow is pointing up, and then as x goes to infinity, f of x goes to -infinity, which means on the right side of my graph, my arrow is pointing down. So that's what each of those pieces mean. Next, for our maximum number of turns, it's going to be 1 less than the degree, so in this case it'll be 4. And then the maximum number of zeros is going to be 5. So that's the maximum number of zeros we could possibly have. We already know we have 3, so we don't have the maximum number of zeros, but that's okay, we don't have to. And the last feature is to look at the vertical intercept, which in this case, again, is 0, 0. So these are kind of all the features that we needed to find. But now we know that we need to come up with our equation. So let's write this up. We're going to have f of x is equal to some leading coefficient, some a value, I'm not sure what, times, let's see, I'm going to put my x in front this time. So I can take this x as an x plus 0, or just an x, and that's going to have a multiplicity of 2. And then we're going to have x plus 3 as a factor, and that comes from right here. We're taking this 0, adding 3 to both sides, and that is also going to have a multiplicity of 2. And then we have the next factor of x minus 3, and that comes from our very last 0, and if you want, you can name that multiplicity of 1. So in order to find our a value, what we're going to do is we're going to use this given point right here of 1, 2. So let's see. Use point 1, 2 to solve for a. Now here's the cool thing. Just by looking at the graph, I can already tell whether the leading coefficient should be negative or should be positive. So I already know that I have an odd degree, and now with my left side up and my right side down, that should mean that I have a negative leading coefficient. So if I go through and I solve and I don't get a negative number, I know I should go back and check my work. So you can use some of your previous information or previous knowledge to help you out here. So basically this means we should get something negative. Let's plug 2 in for our y value. And 1 in for our x value. And let's see what we get. Okay, so we've plugged 1 everywhere we see an x. We plugged 2 for our f of x, which is our y value. Let's go through and solve. So let's see, this is going to become 2 is equal to a times 1 squared, which is just 1. Let's see, 1 plus 3 is 4 squared. 1 minus 3 is negative 2. And again, that's to the power of 1. So this will be 2 is equal to a times 1 times 16 times negative 2. Or 2 is equal to negative 32a. So when I divide that on both sides, I'm going to get 2, negative 2 over 32 is equal to a, and then I'm going to simplify that. This doesn't come out to a super great fraction, so we're going to leave this, or a super great decimal, so we're going to leave this as a fraction, and so that a is negative 1 over 16. But again, don't end here. Rewrite your entire equation. So this will be negative 1 over 16 times x squared times x plus 3 squared times x minus 3. All right. And look, we did get a negative a value, so we know we did this correctly. Let's try it just once more. So for example number 6, we got something even cooler looking. We're getting into even more types of multiplicities, as we can see here and here. So again, I'm going to start with the horizontal intercept so that we can kind of take a look at those multiplicities, and then we'll go back to the degree. So let's see. Horizontal intercepts. In this case, we only have 2. We have them at negative 1, 0 and at 2, 0. So when I list my zeros, I'm going to say x is equal to negative 1 and x is equal to 2. Now when I take a look at these multiplicities, I can see, all right, over here at 2, that's kind of like a bounce or like a little parabola looking thing. So that is going to be a multiplicity of 2. And I totally forgot to write the word multiplicity. There we go. So it's going to be my multiplicities. But around negative 1, we can see it does this weird kind of like, I would call it chair, squiggle maybe, but it doesn't go straight through. It kind of has a little wave to it. This is what a multiplicity of 3 looks like. So we're going to write that as a multiplicity of 3. Now to find our degrees, we're going to add up our multiplicities, and we're going to get another degree 5. And for our long run behavior, we can say that as x goes to negative infinity, fx goes to infinity, and as x goes to infinity, fx goes to negative infinity, which means that on our left side, the arrow is pointing up, and on the right side, the arrow is pointing down. This is the exact same long-run behavior that we had for our previous problem, which means, again, our a value that we end up finding should be negative. If it's not, we should go back and check our work. We got 3 more features to find. And I may have not given myself enough space. Maximum number of turns, again, is 1 less than the degree, so this will be 4. The maximum number of zeros is the same as the degree, so that will be 5. I know we only have 2 zeros at the moment, but the maximum we could possibly have is 5. I'll just list my vertical intercept below because I did not leave myself enough room. So for the vertical intercept, it's no longer at 0, 0. It's actually at 0, -4. And the cool thing is, that's my given point. So right here, at 0, -4, I can take that point, plug it into my equation, and solve for my a value. I couldn't do that with the other problems because it was at 0, 0, which is also an x-intercept or horizontal intercept, but you can use literally any point on the graph other than a horizontal intercept. So using a y-intercept is fine. So use point 0, -4 to solve for a. So let's set up our equation. We're going to have f of x is equal to some a value that we have to solve for times x plus 1 to the power of 3 times x minus 2 to the power of 2. So again, just a reminder, I'm taking a look over here at my 0. I want to set that equal to 0 to get my factor. So I'm going to add 1 to both sides. That's how I got that here, included my multiplicity. Took my 0 here, subtracted 2 on both sides, got this factor, and that has a multiplicity of 2. But let's go through and plug in -4 for our y value and 0 for our x values. So it's going to look like -4 is equal to some a value times 0 plus 1 cubed times 0 minus 2 squared. So that's going to become -4 is equal to a times 1 cubed times -2 squared. See, -4 is equal to a times 1 cubed is 1, -2 squared is 4. So -4 is equal to 4a, divide both sides by 4, and we get that a is -1. Cool. So again, don't end here, take this, plug this back into your equation. We're going to have f of x is equal to -1, or just a negative, that's okay too, times x plus 1 cubed times x minus 2 squared. There's our answer. Okay, that was the last of the new material for Unit 3. So have fun with your Go formative, and then good luck on the review.